Hello, let's start this lecture. So in the previous lecture, we got to the point that we had an equation for the electric field at the aperture of the reflector antenna. So essentially, we had a reflector, and as you remember that we are focusing on paraboloidal reflector, and this is, let's say, our axis, X, Z. Something to be careful. We also discussed the choice of Z, and we mentioned that because this belongs to the feed, you may want to use a subscript F here, and then you have a feed for the reflector right here, and then you get an aperture here, and this aperture is of circular shape, because if this is going to be a circular shape, and this would be essentially the same thing. And then over here we had E over aperture. And then we had this equation for E over aperture, which depended on the feed pattern. It had the 1 divided by R component. It had the phase component, 2F. And it also had the polarization component that we had, UR hat, and R stands for reflection because the mechanism is through reflection, of course. So we had that, and then based on this, we saw that if we write the electric field over aperture, assuming that, for example, this feed is X polarized, and if I want to be very accurate, I could say this X was the same as X subscript F or XF polarized, then your E over aperture is not only going to have X hat, which is your copole, it also going to has Y hat component. So that was the discussion that we had, and you saw that these are related to the E plane pattern of the feed and H plane pattern of the feed. So this was what we discussed in the previous class, and now we're gonna continue with the remaining of the discussion related to this, and hopefully we can understand some more details about the copole and crosspole in this case. So let's continue with the discussion from the previous lecture, from the whiteboard of essentially the previous lecture. Okay, so this is the equation that we have, and now let's have a couple of observations on this equation. So the first observation is that I want to put my feed to be X polarized. For example, this is as we mentioned here. Let me. This is the electric field coming from the horn. You see that this is X-axis. Whether XF or X, they're the same thing. So the feed is essentially X polarized. Now, this is the component that I want. Now, this component makes perfect sense because we know that if you have a flat surface, at least, if you send X hat, the reflection is minus X hat. So, and I see minus X hat here. Remember, this is positive, this is positive. So I have my minus X hat, which makes sense for reflection. So that's one thing. So that negative makes sense. Now let's come here. Now here I have a Y hat. This is my cross pole component. So this is my Y hat is my cross pole component, which I don't want. Now, how can I get rid of my cross pole component? So the way to get rid of your cross pole component would be to make this term 0. And this term 0 essentially means CE theta should be equal to CH theta. So CE theta should be equal to CH theta. And this is the pattern of the feed that looking at the reflector. So if I want to again be very accurate in terms of writing, I need to have subscript F here to say that this is the Z that I'm considering, Z for the feed. So essentially it says the E plane of the feed should be the same as the H plane of the feed. So, and that gives you an idea that why horn antenna are good for the reflector, because their E plane and H plane can become very similar because the dimension could be relatively similar in the E plane and H plane. But if you go with some antennas like dipole antenna, E plane and H plane are completely different. So this essentially say if you use a feed whose E-plane is the same as H-plane, this term goes to 0. Therefore, the whole cross-pole component goes to 0. So this type of feed are called balanced feed. So if you can have a feed that takes this term to 0 by making E-plane the same as H-plane, then you have your balanced feed, which is going to be useful to not have energy in the with this polarization. So this is something to keep in mind. Now let's go and check one more thing. Now, just for the sake of discussion, let's assume that my feed is not like a horn antenna that I can make these almost 0, but I'm going to assume that I have a dipole antenna. So I have a dipole antenna, and I'm going to put my dipole antenna along x-axis. So this is my dipole antenna. Now, what is the CE, the E-plane of dipole? Is cos theta. What is the H-plane of dipole? It's essentially omnidirectional, is the same everywhere, so 1. So I'm going to have E-plane of dipole cos theta, H-plane of dipole 1. And I could be accurate here to just say cos theta F, and this is 1. So if I go with dipole, I can substitute that by cos theta F. This is with 1. And let's see what I'm gonna have. So let's remove this and put cos theta F, and let's remove H-plane and place 1. So cos theta F minus 1. So that's what we have. Okay, so now what's the situation here? I'm gonna have a y hat now, but can I decrease my y hat using a method? So something that you notice here is that if you want to, because this is gonna be here because it's not balanced, so y hat is gonna be, you're gonna have a y hat component anyways. But how can you reduce this? So remember, if I increase my FD, sometimes I use diameter with a small d, sometimes I use capital D. So I mean, both of them the same for me, a small d or capital D in this context. So if I increase my F divided by D, remember curvature reduces. So imagine, for example, if this is my reflector for 1 divided by 4, for half F divided by D, this becomes that. So if you look at your theta F, which are these angles, so in this case, theta F can goes to 90. And if it goes to 90, it maximizes this because this becomes 0, cos of 90, 0 minus 1 becomes minus 1. But now, in this case, so it is going to be much less. Maybe I even have the number for this. So I don't, unfortunately. So the theta F, you see that it becomes smaller. So what you see here is that if FD becomes larger, the range of cos theta F becomes more confined. And if the range of theta F is very small, for example, from 0 to 20, for example, then cos of theta is going to be close to 1 because, you know, around 0, this is extremely close to 1. So 1 minus 1 could be 0. So that essentially means that if I increase my F divided by D, I can bring this bracket down in terms of value. Therefore, I can reduce cross polarization. So keep the FD up, you can bring down the cross polarization. So that's one observation here. Now, let's make another plot here and see how this plot looks like. So what we're going to do is that we're going to plot the electric field over the aperture of this reflector antenna. So let's have our coordinates again. This was my X. Now, this is Z for the reflector, for the radiation. This was, of course, ZF. This was YF. And this was Y. And X and XF were the same thing. So you can check X, Y, Z. So this Y and YF are different. X and XF are the same thing. Now, aperture, this is my aperture right here. So I'm just gonna plot my aperture. So let's plot the aperture here. So this is gonna be my X. This is gonna be my Y. So X, Y, Z toward you. So that's gonna be behind, let's assume behind this wall was the reflector, and reflector is radiating toward you. So X, Y, Z is the radiation. So I'm essentially plotting this cross section, and I want it to be consistent. So X and Y, so and this is X and Y. And we said that it's gonna be a circle. So let me have my circle. The radius of the circle is, of course, d divided by 2, the diameter divided by 2. I have that here. And it's also useful to notice that this is going to be the same as your XF, but then YF is in this direction. So that's my YF, is opposite to Y. Now, let's start plotting. So the question is, what's going to happen first if I'm on the x-axis? If I'm on the x-axis, if I'm on the x-axis, which is the same as on the xf axis, then my phi f is 0. So phi f is 0. If you are on the negative side of that, phi f is 180. So you see that as soon as phi becomes 0 or 180, this term goes to 0. So you essentially lose the whole cross polarization when you are on the axis. So what remains would be just this numbers times negative. So negative rotates in the negative direction. This was in the positive x feet. This becomes now negative x. So this is going to become your electric field over x. So this is going to be the electric field over x. So negative x hat. Now, what happens if you are on the y-axis? If you are on the y-axis, positive y is the same as being on the negative yf. So phi f becomes 270. If you are on the negative y, it's like being on the positive yf. So phi f becomes plus 90. So if you are on this line, essentially this line, phi is either 90 or 270. As soon as it becomes 90 or 270, this goes to 0. So cos of that is 0. So this whole thing goes to 0. You're essentially going to have only, again, minus x hat. So this is going to be your electric field, like this. So this is beautiful because you see that in these two cuts, there is no cross pole. So there is the cross pole is completely absent here. Now, let's assume, for example, consider a point here. So if you consider a point here, this would be interesting because now you see that in this point, you are on the positive side of XF and on the positive side of YF. YF is in this direction. So if you are on the positive side of XF, positive side of YF, sine of phi f, cos of phi f would be positive, both of them. So this is a positive number. But remember, this is going to be a negative number because cos is going to be smaller than 1 anyway. So this is a negative number. So you get a negative y hat. This was positive. This becomes negative, negative y hat. And negative y hat, this is the direction of y hat. So negative y hat would be in this direction. So you're going to get a cross-pole component in this direction, and you still have your minus x hat. So this becomes the electric field at that point. You're going to start having cross-pole. So now let's go, for example, somewhere here. So if you are somewhere here, you see that your XF is positive, YF is negative because YF is in this direction. So if your xf is positive, yf is negative, that means your sign becomes negative, this becomes positive. So this is a negative number. This is always a negative number. Negative, negative, positive, you get a positive y hat. But y hat is in this direction, so you get your y hat here. You are still going to have your minus x hat. So that would be the situation there. Now let's bring our point to here. And what's going to happen here? In this point, xf is negative, but yf is positive. So when you are at this point, then again, this is going to be negative for you. This is going to be negative for you. This was negative all the time. Negative, negative, positive, you get positive y hat. So you get positive y hat. Remember, y hat is in this direction. And then you have your minus x hat still. And now let's go to this point. Now you get xf. This is the positive xf. This is negative x. This was positive y. So this part is negative yf. So this becomes negative, negative. So this becomes a negative number. This becomes negative number. In total, they're plus. This is negative always, plus, negative, negative. You get negative y hat. So this was y hat, so negative y hat in this direction. You are still going to get your minus x hat. So this is going to be the situation that you have on this aperture. So you see, you have bunch of very beautiful electric field all in the minus x hat direction. But then you get these things that they actually in the opposite direction, so they're not useful for us for radiation. So look at this, opposite direction to this, or this y hat opposite direction to this, but the remaining x minus x hat component are so in the same direction and very good for us. So we want to reduce this cross pole effect by using balanced feed, or if we cannot have a complete balanced feed, maybe we can increase our f divided by d so that we can decrease y hat, because this effect, this essentially has a negative effect for us based on this explanation. Okay, so we just saw what happened with the cross-polarization component, and now we need to continue our discussion with the remaining parts of the reflector antenna. So, let's in the beginning, let's talk about the directivity and how we can understand directivity. So imagine, let's start with that equation that we always use, 4 pi lambda square, and then aperture efficiency, then physical area. So this is the equation that we have for directivity. So if this is our reflector, this is the axis, and this is our x, this is our z. If I want to be very careful here, perhaps I'm going to say that this is the x and f corresponding to the feed that I'm having here, and this is the aperture that we just studied for the cross polarization. So I mean, it should have the same dimension. So it's a little big here. I need to make it a small, and so like that. Now, what is the physical area? We learned that this is in fact a circle. So let me plot the circle for you. This is my xf. So if this is x, this is z, this would be y. So this is my yf. But just to remind you, this was the z for the pattern. So this was y. So this is y, the other y. So I mean, it doesn't matter for this discussion right now. But remember, this is a circle. So and the diameter of this circle is d, or capital D. Therefore, the physical aperture is pi d squared divided by 4, and then we need to study the aperture efficiency, of course, to understand its directivity. So to do that, let's first remember our open-ended waveguide antenna. So if this was our open-ended waveguide antenna, we had something called amplitude taper. So this amplitude taper was essentially saying that this is the electric field over the aperture of the waveguide. You're not using the whole aperture, so these parts are essentially not used because you have a taper. And remember, we had this equation for aperture efficiency for the the way that we calculated was, we said maximum effective area is E tangential ds to the power of 2 E tangential 2 ds. So that was our effective area. So you can always divide it by physical area of the waveguide in this case. So you divide by physical area, and this became aperture efficiency. And for the open-ended waveguide, it was 0.81 or 81% that we had. So you see, because you had this amplitude taper, you had uh, instead of 1, you had 0.81. Now, when we go to reflector, this is the same situation here. If you are on this axis, remember the drop here is 1 divided by, if this is R1, R1. If I go here, it becomes, if this is R2, this becomes 1 divided by R2 in terms of amplitude, and so on. So if this is R3, this becomes 1 divided by R3. So this is the situation that we have. So you see, we don't have a uniform amplitude exactly like this. And so one way to do that is that you could perhaps control this a little bit with the pattern of your feed. For example, you might say, I'm gonna send more energy from the feed to this edge, to this area, because this R1 is essentially for it's going to be bigger than this, for example, R3. So this is a smaller here. So I'm going to have more energy in this direction, because remember, this is going to be multiplied by the pattern of the probe. So it's not just 1 divided by R1, you have the pattern of the probe too. So that's one thing you could do. But remember, if you want to send more energy to the edge, you're going to have other problems. First of all, you get some diffraction effect from the edge. So you get your diffraction effect from the edge. The other thing that's more major is that if the energy, you have lots of energy here, so imagine there is a good lobe here, and then some of the energy is completely lost. So this is a spillover problem, that you're gonna lose some of your energy, and in some situation you need to essentially make sure that you're not losing any energy. For example, so in scenarios that you don't have enough power, or they may interfere. So you don't want to send much energy in this direction. You want to have it more in this direction, so that most of the energy would be reflected back and you don't lose energy because of a spillover. So, but the point that I'm making here is that part of this aperture efficiency for the reflector is also related to this taper situation that we have, that the fact that the amplitude is not uniform here. So we may refer to this as a taper efficiency here, and maybe we call it as eta T for taper in this case. So this is part of the story. But again, if you look at for example our waveguide, the thing is, everywhere is metal. So the energy that you're putting into the waveguide is traveling, and you don't lose your energy within the waveguide. It's just metal. But what happens with reflector, that's not the situation with reflector, because in a reflector, what's going to happen is that you have a feed, and if this feed has a pattern like that, so you see that this part of the energy, if I think of ray, is not going to be intercepted by the reflector. So here, this is a waste for me. Would be a waste for me, and I'm just going to have the situation that's this rays that are going to be reflected by the reflector is going to contribute to my far field pattern. This stuff is going to be lost. And this is something that we call a spillover efficiency. We need to know how much we are efficient in terms of a spillover. So I can just write here that another component of this is a spillover efficiency. So we already learned about this taper situation. Now, if we want to talk more about a spillover efficiency, we might represent it by eta S, for example. That's another component of this. And so if we consider a spillover efficiency, we see that we can essentially say power intercepted by the reflector divided by the total power. So this is the situation that we have. And how can we find the total power? Let's start by total power. So we're going to have F theta and phi. This is going to be a squared. So this is my pattern. And then it's going to be over the solid angle. So sine theta, d theta, d phi. So this is what I have. And I'm going to integrate over the whole domain when you know theta is from 0 to pi and phi is from 0 to 2 pi. Now, if I go to the numerator, which is the power intercepted by the reflector, I'm going to have the same thing. So that makes it power. But then when you have sine theta, d theta, d phi, you need to be careful because first of all, phi, this is axis symmetric. It's a parabola. You rotate it about the axis. So phi is still 0 to 2 pi. No problem here. The same as that. You just need to be careful that your theta is not 0 to pi, because if you go 0 to pi, you go from here all the way to here. So that would be the total radiation. Even for example, you are considering back lobe and all the lobes here. But the one that's going to be intercepted would be essentially to this theta naught, starting from here to get to this theta naught over there. So essentially this becomes 0 to theta naught. So the main difference here is that this is 0 to pi, this is 0 to theta naught. So this is something that you need to consider. And theta naught connect the focal point to the rim of the reflector. So this is the rim of the reflector, you get theta naught. And this way you can calculate the spillover efficiency. Now, if we think about this, let me also make a comment here that again here when we talk about theta, for example, this theta that we have, we are calculating theta with respect to this z-axis. So if you want to be very careful, you need to refer to that as theta f, for example. So this is going to be theta f because that would be with respect to this z, which is in fact zf. But I just relaxed it here a little bit, but make sure you know that because the other z is this z, and if you look at that, this is the theta with respect to this z, but with respect to this z, this is going to be 180 minus theta naught. So you just need to be careful about this. Of course, here we talk about feet, so our coordinate is related to the feet. Now, at this point, something is missing. If you know the pattern of your antenna, you can actually calculate that based on this equation. But then you might say, how can I calculate theta naught? So this is something that you need to know. And after you know that, assuming that you know the pattern, you can plug it here. And then by knowing theta naught, you can actually find these two and have your spillover efficiency. Now let's talk about this theta naught, how you can calculate that. So this is my reflector again. This is my X. So I know that R is 2F 1 plus cos theta. I want to emphasize here that again, I'm in the feet coordinate. So I probably should use Z subscript F, X subscript F, R subscript F, theta subscript F to emphasize that. But let's assume that this is implicit in my discussion at this point. So now if I have that, then what is my theta naught? This is my theta naught. Now, you know that if this goes to the rim, and theta naught means it goes to the rim, then this height here is d divided by 2, where d is the diameter of the reflector. So based on this, I know that d2 is r sine theta naught. So this is what I know, and it's r sine theta naught, and I can also write that as r naught to emphasize that this is the r that goes to the rim. So r naught sine theta naught is going to be d2. So here I can actually evaluate this at the rim. So that's going to be r naught 2f 1 plus cos theta naught. And to get to this equation, I'm going to multiply both sides by theta naught. So r naught sine theta naught is going to become 2f sine theta naught 1 plus cos theta naught. 1 plus cos theta naught, I can write it as 2 cos square theta naught divided by 2. Now, this 2 and this 2 cancel. And then I'm going to write this sine as 2 sine theta naught divided by 2 cos theta naught divided by 2. Based on this, I can cancel one of this cos with one of the cos here, so this 2 would be gone. So now what I'm going to have would be 1 cos here, and I have this, and I can also convert this to sine theta naught to cos theta naught to, and let's see what I'm gonna get here. So let me check. This was already d divided by 2. So yeah, that's a step that I missed. I know that r naught sine theta naught is d divided by 2, so I'm going to remove this and just plug d divided by 2. That's going to bring me to d divided by 2 equal, I have a 2 here, and sine theta divided by cos theta, that's going to make tangent. So that's going to be tangent of theta naught divided by 2. Therefore, tangent of theta naught divided by 2 is d divided by 4. And I missed an f here. I had an f. So there is an f here. So therefore, this f goes to the denominator like that. And then I can say theta naught becomes equal to 2 times tangent minus 1 d4f. So this is going to become my theta naught. So tangent minus is a tangent. So 2 times tangent minus d divided by 4f. That becomes the angle theta naught. Now let's check this equation, see if I made any mistake or not. The one that you can always check is by the case where we know how the reflector looks like. So we know that if f divided by d is 1 divided by 4. This is the shape of the reflector. So in fact, the rim would be on the x-axis. So theta naught becomes 90 degree if f divided by d is 1 divided by 4. Now let's plug here. So theta naught becomes 2 tangent negative 1 d divided by 4f. Let's write it as 1 divided by 4 fd. That's going to be 2 tangent minus 1, 1 divided by 4. F divided by d is 1 divided by 4. So that becomes tangent minus 1. Tangent minus 1 of 1, which is 45 degrees. So 2 times 45 degrees, that's going to make it 90 degrees. So this is a correct equation. So this is essentially what's going to happen is that if you have a pattern and you want to find the spillover efficiency, you can easily do that by knowing the pattern. You perform this integration, and when you look at that, just have this in mind, that we said total power radiated is u d omega. So this is essentially talking about the same equation. So that's the element of solid angle, and you just continue by integrating over the whole space. But then here you need to integrate to theta naught, and you can know your theta naught if you know the ratio of f divided by d. You can plug it here to find your theta naught. Then you just find the power that's going to be intercepted by the reflector. Okay, before we continue, let me have this equation a little bit better. Remember, when we say f squared, the purpose here is to get to the power. So this is the feed pattern, you want to get to the power. But remember, when we are dealing with complex number, we need to be careful. It's when we say a square, to get to the power is magnitude a square. So I need to write that as magnitude of f a square. When f is complex number, then magnitude makes it real. Real to the power of 2 would be real. So these are magnitude of f squared that we have. So this is our spillover efficiency. So we saw that we have this taper efficiency and so on. The other one that we have is, so these two are important. The other one that we could have here is the achievement efficiency. So this consists of several sub-factors. For example, consider this case that you have a reflector, and then this is your feed. Of course, when this is your feed, and consider this ray, it's going to come back here, but then you have this feed here, so it's going to block the reflection. So this is related to blockage. So a part of achievement efficiency would be, for example, related to blockage of the feed. This is one source of error, and maybe at this point it's not a bad idea to mention that when you are dealing with this type of blockage, one option that you have is to, if this is your reflector, you're only going to consider part of the reflector, and this used to be your focal point. Now you have your feed, but then you rotate your feed in a way that instead of looking at the apex, it somehow, it's almost at the middle of this section of this curve. So this is, if that happens, you can have a situation like that. So therefore you don't have any blockage in this case. So this is would be one method to not have the blockage. And if you look at the measurement video that I had, in one video I'm showing a compact antenna test range, and in the compact antenna test range you actually see a feed and with the reflector, and this is the configuration of the compact antenna test range that I showed in one of my I think that would be the second part of lab 1 toward the end. So that would be the blockage efficiency, and so this would be one part of it. The other part of it would be, for example, surface error that we might have. So remember, this paraboloid needs to be r equal 2f 1 plus cos theta. Now, during the fabrication, if you deviate from this, then of course you're going to get some problem. And when you are dealing with large reflector, maybe they made of different panels and they need to be connected to each other. So you essentially need to be careful about that. And anything related maybe to phase issue of phase center. So for example, if you have an antenna, you want to place its phase center right at the focal point. So if you deviate from that, that's going to contribute to the achievement efficiency. So you see, you have this essentially consists of this multiplied by that, multiplied by this one. So it's three main terms we have. And if you, for example, wonder about a typical gain value, aperture efficiency value that we have in reflector, you may think of something approximately between 55% to 65% aperture efficiency. So here I think I forgot to talk about another one, which is the cross-polarization effect. Imagine your feed has a cross-polarization component. In the previous discussion that we had about the feed, we assumed it was purely polarized along x-hat, but if the feed has cross-polarization, it's going to contribute into the achievement efficiency. So the cross-pole would be another one. But anyways, in total, you're looking about 55% to 65% aperture efficiency as a typical value. So this would be our discussion about this aperture efficiency, and you can now compare it, for example, to 81% that we had for the open-ended waveguide. That does not mean open-ended waveguide antenna is a more directive antenna. Remember, although the aperture efficiency is smaller than open-ended waveguide antenna, around 81%, but then open-ended waveguide antenna had an aperture, physical aperture. So if this was open-ended waveguide, you remember approximately this was 2 lambda by 3, this was lambda by 3. So the aperture size is relatively lambda by 3 approximately. So it was very small, but now you may have a reflector where this is 30 lambda. So now if you look at the area, physical area in this case is 2 lambda by 3 times lambda by 3. But in this case, you're looking at pi d squared divided by 4. So you get pi 30 to the power of 2 would be 900, and lambda becomes lambda squared divided by 4. So you see that you're going to get a huge physical area here, because this equation is essentially aperture efficiency times physical area. So you have good aperture efficiency for OEW, but then your physical area is small. Now you get to a smaller aperture efficiency here, but then your physical area is much larger. And in this case, the physical area is the main thing here. So now this also opens up our discussion regarding reflector design, because as is noted in the textbook by Professor Stutzman and Thiele, what we have in terms of reflector design, a major contributor is essentially related to trade-off between these two. Because if you have a very directive antenna, so I think a better representation of that can be found in that textbook. But if you have a very directive antenna, of course, you're not going to have much spillover. So your spillover efficiency would be nice, but then you're going to lose on the taper efficiency. Whereas if you do a wider beam, then the situation is reversed. You're going to win on the taper efficiency, but you're going to lose on the spillover efficiency. So essentially, the adjustment of these two is a very important contributor, and that needs essentially we get to a trade-off between these two components. Okay, so to maximize our aperture efficiency, as we mentioned, we have a trade-off between spillover efficiency and taper efficiency. Now, if you study this in more details, you're going to see that to maximize that, we need to have this situation that if you have your reflector and you have a feed like that, then this is apex. So if the electric field arriving at the apex is normalized, let's say to 1, when it's going to get to the rim, it should be get to 0.28%. So 0.28. So this is essentially the ideal number maximize the aperture efficiency between as a trade-off between these two. So if I convert this to dB, because this is electric field, I'm going to do 20 log. So 20 log of 1 is 0 dB. 20 log of this is minus 11 dB. So you essentially want to have a situation that when your feed is illuminating the reflector, the field here is 11 dB less as compared to the apex. So that's the situation, and this is essentially, you may refer to this situation as matching the feed to the reflector, that you want to satisfy this. And this is you can refer to that as EI, edge illumination. So you say, I'm going to have an edge illumination in this case, for example, equal to minus 11 dB. So this is essentially the process of matching your feed to the reflector, that you want to have a certain number dB less compared to apex. And in this particular case, we wanted to have a trade-off so that we maximize that. And the answer for us is minus 11 dB in this case. So I'm going to work on this more in the next section to see how we can use this to find the parameters that we need for our reflector antenna. So that would be discussed in more details later on. So for the sake of time, because I won't be able to cover the whole thing regarding this, let me do one geometrical example, which is separate from this, and then we focus on this more in the next class. So to focus a little bit more on this, to focus more on the geometry, let me ask this question, that you have this reflector, and this is your focal length F. This is D, diameter D, either capital D or a small d. And this is essentially called the height of the reflector, H. So let's calculate the height of the reflector and see how we can find it based on F and D. So to do that, we need to know the coordinates of this point at the rim. So if this is Z, this is X. Again, I'm emphasizing here that these are feet coordinates. So you might want to have a subscript F here, but let me just keep it like that for simplicity. This is my Cartesian equation for the reflector. And this point, in terms of X, it is D divided by 2. So this is X, this is D divided by 2. So that's my X. If I'm in this plane, my Y is 0, because based on that, X, Y, Z, this is your Y. Again, this is YF, this is XF, this is ZF, just to be clear. So this is my Y0, and what about my Z? My Z at this point, this is a focal length, this is height, so this becomes F minus H. So the only thing you need to do is to substitute this here. So X is D divided by 2 to the power of 2, becomes D2, 4, plus y2 is 0, equal 4f, f minus z, f minus f plus h. So f and f cancel, and you're going to get height equal to d2 divided by 16f. That becomes the equation for the height of the reflector. So now that we know the equation for the height of the reflector, we can test it for the simple example that we always do. So we know something that we can verify equation with. We know that if F divided by D is 1 divided by 4, this is going to be our reflector. So essentially the rim meets the x-axis here. So this is a particular case, because if this is focal length, then the height of the reflector is equal to focal length. For example, in this case, focal length is greater than height, but in this case, they're exactly equal. So now let's check that. If I place F divided by D equal 4F, perhaps you can just substitute your D by 4F based on this there. So your H becomes D squared, but D is 4F. It becomes 16F squared divided by 16F, which is going to be just F. So we just proved that H is equal to the focal lengths here. So that's just another thing that we need to calculate. So in summary, we also learned that we also learned two geometrical things. One of them was this theta naught, the angle to the rim, and this height here. So in particular, this is very important when you are calculating for this spillover efficiency, and you might also need to calculate the height in the final exam. Okay, so I think that's it for our lecture for today, and in the next lecture we're gonna complete our discussion by focusing more on this edge illumination.